Hello everybody, hope everybody is doing great. CRS here. I have brought another video for you today. It discusses about acceleration due to gravity and its variation with height, depth and latitude. Let's begin with the video. So we have the earth and the center of the earth, let's say, is here. Mass of the earth is capital M and you are standing on the surface of the earth. Let's say your mass is small m. Now, what is the distance between the place where you stand and the center of the earth? It's quite an easy answer. You can say that, sir, the distance between myself, who's standing on the surface of the earth, and the center of the earth is equal to the radius of the earth. Now, in the previous video, we had seen how to apply Newton's universal law of gravitation. It said that the force acts between the centers of the two bodies which are mutually gravitationally attracting. So when that is the case, you can write Newton's universal law of gravitation, which says that F is equal to G times m1 into m2 divided by r square. m1 here is the mass of the body which is on the surface. I have said that it's yourself, and capital M is the mass of the earth divided by r square. R is the radius, which is the distance between you and the center of the earth. When that is the case, there is a force acting on both of you. Earth is really massive, it wouldn't move. It's you who would move if you dropped yourself from a certain height, or any body for that matter. We have force acting on the mass small m being equal to small m into acceleration. This acceleration is due to gravity, so you would write m into g. F equal to m into acceleration, which is acceleration due to gravity, g. It's equal to g small m into capital M divided by r square. M and m gets cancelled. The acceleration due to gravity becomes equal to g capital M divided by r square. This is the equation for acceleration due to gravity, and we must remember it. This is not just for the earth, this is true for any planet. You just need to know the mass of the planet and the radius of the planet. You end up calculating the acceleration due to gravity. On the surface of the earth, dear friends, g is 9.81 meter per second square. What this means is, any body that is dropped at a point near the surface of the earth, irrespective of its mass, will fall to the surface of the earth at this rate, 9.81 meter per second square. That means, to put it in simple words, in the absence of air, if you dropped a hammer and a feather from the same height, they would hit the ground exactly at the same time. Now, having shared that with you and having derived the formula for acceleration due to gravity at the surface of a planet, when I say planet, every time that comes to my head is the earth, and that's a general formula. It can hold for any planet for that matter. Let us look at a question based on what we have just now learned. The question goes this way: a body has a weight of 90 kg. The question says 90 kg. You might be confused. 90 kg is the mass, sir. It's not the weight. Correct. But what the question is trying to tell you is it's 90 kg weight. That's what it is. Okay. So we can write the weight of the first body, W1. The body is 90 kg weight on the surface of the earth. The mass of the moon, maybe I'll just write this as WE, which means weight of the body on the surface of the earth. The question says that the mass of the moon is 1 by 9 of that of the earth's mass. So mass of the moon is equal to 1 by 9 times mass of the earth. The question continues. Its radius is 1/2 of that of the earth's radius. The radius of the moon is 1/2 of the radius of the earth. This can be implied as mass of the moon divided by mass of the earth is 1 by 9, and here radius of the moon divided by radius of the earth is 1 by 2. These ratios will prove themselves useful in the process of solving the question. On the moon, the weight of the body is, let's try to figure this out. Let us write an equation for acceleration due to gravity on the surface of the earth. You have G equal to G, capital G, into mass of the earth divided by square of the radius of the earth. So we will write small re square, and acceleration due to gravity on the moon becomes G m mass of the moon divided by radius of the moon square. If you just divide these two equations, let me divide equation 2 and equation 1. When you do that, you have Gm divided by Ge, which is going to be equal to mm divided by me multiplied by Re divided by Rm, the whole square. It's time to substitute. We have Gm divided by Ge being equal to mm by me is 1 by 9. So you can write 1 by 9 multiplied by Re by R. Rm by Re is 1 by 2. Re by Rm would be 2. So you have 2 square. The answer for this ratio would be 4 divided by 9. If you just multiply and divide by mass of the body in this equation, nothing about the equation changes, but mass of the body into acceleration due to gravity gives you the weight of the body. Having shared that with you, now you can simply write this equation as, let me continue that here, the weight of the body on the moon divided by weight of the body on the earth. Weight of the body on the earth would become equal to 4 divided by 9. So it would be 4 divided by 9. So what would be the weight of the object on the moon then? The weight of the object of the moon then would be equal to 4 divided by 9 multiplied by weight of the body on the surface of the earth. We has to be multiplied, but you can see We has been given to you as 90 kg weight. So let's substitute that 90, and so this gets cancelled. We have weight on the surface of the moon being 40 kg weight. 40 kg weight, my dear friends, is the weight of the body on the moon, and that happens to be option D. Option D is the correct answer. These questions that I get for you are genuinely from various competitive exams across the country. So it is important for you to be able to solve all of these questions. These questions are quite simple to begin with. These set of videos initially that I'm supplying to you on a daily basis is for you to get through all the regular competitive exams. JEE Mains is an exam of a little higher order, and advanced is certainly something that will require a good proficiency with respect to conceptual understanding, but this will form the basis for everything. Let's go to the next concept. This is a concepts demonstration. You can find so many questions. If you don't have, you can write to me and I'll send you a worksheet for whatever concept that you need, and you can practice that. Let's go to the next concept. The concept is about variation of acceleration due to gravity with height. Now, how does the acceleration due to gravity change with height? That's the question. Let's figure out. We have the earth, that's the center of the earth. This is the surface of the earth. Let's say you have gone to a height there. That's the point at which you want to measure. This is the point. Let me call that point A, and that's where you want to measure the acceleration due to gravity. Let's write down all the distances. So you have this being the center, that being the surface, and this one being the height of the point from the earth's surface. Let us mark these distances. From here to here, it is the height h, and from here to here is the radius of the earth. We know what is the acceleration due to gravity on the surface let me say that the acceleration due to gravity on the surface is g, and the acceleration due to gravity at that height h is g dash. Now we need to write a relation between them. Let's try to do that. From the regular equation for acceleration due to gravity that we just derived, g would become equal to g capital M divided by r square, where r is the radius of the earth, r square, where r is the radius of the earth. Maybe we should call that equation 1. And let's also write down an equation for acceleration due to gravity to that point A, which is g dash. The acceleration due to gravity at that point is g dash. So g is the same, mass of the earth is the same, but then the distance from the center to that point A is r plus h. So you would write r plus h the whole square, r plus h the whole square. We will call that equation 2. Let's divide equation 2 and equation 1. You would have g dash divided by g, gm and gm will get cancelled, and you will have r square divided by r plus h the whole square. I think this is certainly an important equation. G dash is the acceleration due to gravity at a height, g is the acceleration due to gravity at the surface, and they are related as r divided by r plus h the whole square. But then you can come back to me and say, CRS, this is a very tedious calculation to do. Every time you have the numerator and denominator, I have to square it and then multiply it with g, divide it, and a lot of things to do. Can you give me a simple formula? I can, but with a constraint. The constraint is that we can go further if the height that you're talking about is very small when compared to the radius of the earth, then something can be done. Let me show you what can be done. Well, let me continue to write on this part of the board. Well, when h is very less when compared to r, you can pull out r as a common factor and cancel it out. You will have g dash is equal to g into r square will come out from the numerator and r square will come out from the denominator. What you have inside is, anyway, r in the numerator has come out, so there is 1, and then there is r plus h, 1 plus h divided by r the whole square is all you will have. 1 plus h divided by r the whole square is all you will have. Now, if you move this whole denominator up, of course r square will get cancelled. G dash would become equal to g multiplied by 1 plus h divided by r raised to the power of minus 2. Let us now go ahead and simplify this. G dash would become equal to g into 1 minus 2h divided by r. That's a binomial expansion. The first term has been taken, the rest of them are too small, so we have neglected them. The minus 2 gets multiplied with h here, so minus 2h divided by r. This is an equation that can really serve you well. This is an equation that can serve you well only if h is very less when compared to r. Otherwise, in all other cases, you will always use this formula. These are two relations that will prove really useful when you are solving numericals, MCQs related to variation of acceleration due to gravity with height. One thing that you need to remember is acceleration due to gravity at a height, at a place away from the surface of the earth, varies inversely as the radius, inversely as the square of the distance between the center and the point you are talking about. Anyway, look at this equation. I was referring to that. G is inversely proportional to distance between the center and the point. That's the equation I was referring to. But anyway, let's go to the next question, which demonstrates the concept that we've just learned. The value of G on the surface of the earth is 980 centimeter per second square. So acceleration due to gravity on the surface of the earth is 980 centimeter per second square. The question says the value at a height of 64 kilometer. Now you need to understand that height of 64 kilometer is a very small height. From the earth's surface is, that's the question. What is the acceleration due to gravity at a height of 64 kilometer? 64 kilometer is really small. So when compared to the radius of the earth, which is 6,400 kilometers, you can write down the equation g dash is equal to g multiplied by 1 minus 2h divided by r, where r is the radius of the earth. Having said that, we have g dash equal to g is 980 anyway, 1 minus 2h is 64 kilometer divided by radius is 6,400 kilometer. I did not convert the units because these two are in kilometer and the units will anyway get cancelled. So this will become 100 and g dash will become 980 multiplied by 1 minus 0.02, which is 980 multiplied by 0.98. Turns out to be option A. If you multiply that, 960.4, 960.4 meter, centimeter, 0.4 centimeter per second square. That's the answer you would land up with. But anyway, if you calculated the same result with the formula G equal to G dash into R divided by R plus H the whole square, you would get exactly the same answer. But then the calculations could get a little harder to do, and that's why you would use this equation. Otherwise, it is always this, repeating it multiple times so that you don't miss this point. Let's go to the next concept. Variation of acceleration due to gravity with depth. Now, when you dig into the earth and you stand at a place there, what would be the acceleration due to gravity at that place? Now, that's the next thing that we are going to do. Let's say on a fine Sunday morning, you decide to dig into the earth. So you've dug into the surface of the earth. This is the center of the earth. Let me just paint it black so that you will know that we have dug deep into the earth. Well, having said that, if I ask you, you must be standing on some surface. What is the surface on which you are standing right now? You would probably answer by saying, sir, it is this surface that I am standing on. It is this surface that I am standing on. Maybe you can just imagine that you're standing on a smaller earth after digging deep into the earth. Let's assume that you want to calculate the acceleration due to gravity at this point, at the depth here. Let's write down all the distances. This is the center. This is the place where you are, and that's the surface of the earth. Well, the distances would be from here to here is the depth d, I shall write, and from here to here is the r minus d, because this whole distance, by the way, all the way from here to here is r, the radius of the earth. So having said that, this whole distance is r, so you dug into the earth to a depth d. The sphere, the surface of the earth on which you are standing on, has a radius r minus d. Well, having shared this idea with you, let us now continue and talk about the acceleration due to gravity. It's quite simple to understand that on the surface, acceleration due to gravity is g, and it has always remained the same, which is g equal to capital G m divided by r square, where r is the radius of the earth and m is the mass of the earth. Then, what is the acceleration due to gravity at that point? We will have to figure out. But before we figure that out, let us express, because the mass of this part of the earth, when you're calculating g, is not the same as the smaller earth on which you're standing when you have dug deeper into the surface. So masses are different, so it would be difficult to compare. So let's write everything in terms of density. Let's give that a try. Mass, my dear friends, can be written as the product of density and volume. Density is 4 divided by 3 pi r cube, because the radius of the earth is r, multiplied by density. So density is rho anyway. I shall write that rho. Substituting it there, we have G being equal to G divided by R square into 4 divided by 3 pi. I shall write that rho and then R cube. There is a square and cube getting cancelled. When that is the case, G becomes equal to 4 pi rho G multiplied by R. This is the expression for acceleration due to gravity for any planet in terms of its density and radius. Now, I told you that you've dug deep into the surface of the earth, you've gone to a depth d, you are standing on a smaller earth of radius r minus d. Let's say the acceleration due to gravity at that point, at this point, is g dash. Now, what would be g dash? G dash would be similar to this. It is 4 pi rho g multiplied by r minus d. Multiplied by r minus d. Going further, you can now write a relation between g and g dash. Let me call that equation 1 and equation 2. Let's divide both the equations. If you divided both the equations, you will have g dash by g equal to 4 pi rho g multiplied by r minus d, whole thing divided by 4 pi rho g multiplied by r. 4 pi rho g and 4 pi rho g gets cancelled. All you will have is r minus d divided by r. Let me complete that in this part of the board. All I have now is g equal to g dash. G dash equal to g multiplied by, you can split the denominator, r by r minus d by r. You have 1 minus d divided by r. That's an important equation. That's an important equation. Now, having shared that with you, let us try and solve a problem based on this. I know that you could be watching this video either when you are in first year or you are in second year, but it's important to know how to derive a certain quantity, because in the exam, any derivation can be a question. So if you have the hang of solving questions by means of deriving formulae and not by hearting them, your preparation has already gone a long way. So remember to get the formula before you use it. That's the mantra. To remember all formulae you want to remember, shortcuts will occur to you without anybody's help. That's my suggestion. Let's go further. We have a question now. The depth d at which the value of acceleration due to gravity becomes 1 by n times the value at the surface. So we want the acceleration due to gravity g dash to become 1 by n times the acceleration due to gravity at the surface. Now, how do you go about this? We know that g dash is g multiplied by 1 minus d divided by r, my dear friends. And that's equal to 1 divided by n into g. The right hand side has remained the same, but g and g gets cancelled. Then 1 minus d by r will go this way, and you can get 1 by n to this place. You will have d by r on the right hand side. Let me write d by r here, and then what you have on the right hand side now is n minus 1 divided by n. So this simply implies that the depth now is n minus 1 divided by n multiplied by r, which is the radius of the earth. Let's see which option matches the answer we've got. Quite clearly, that's option B. Now, going further, this is a easy demonstration, but as I told you, these questions could seem very easy, but they have occurred in various competitive exams all over the country. So you need to solve these questions first before you get into solving the harder ones. Let's go further. Variation of acceleration due to gravity with latitude. Now, how does acceleration due to gravity change with latitude? Let's try to figure out. Well, if you see, the center of the earth is here, and you are farthest from the earth when you're farthest when you're standing at this point. When I mean farthest, I mean when you think about a circle, if you're on the equator, you're actually making the biggest circle. You're actually making the biggest circle. But if you are at some other latitude, let us say you are at some other latitude, let's say this latitude, right? If you are in this latitude, then what happens is you are not going in this bigger circle, but you are going along a smaller circle. Here it will be even smaller. At the poles, you are not going in circles at all. So you're simply turning at the place where you are on the poles. But anywhere else, you are going in a circle. And whenever you are going in a circle, you will experience a centrifugal force, because of which the total acceleration that you would experience towards the center of the earth would change. Now, that's exactly what we are trying to compute with this particular exercise. Let us try and understand that this is the radius of the earth. I've drawn the radius of the earth. Let me mark that as capital R. That's the radius of the earth. The latitude of the place is the latitude of the place of this place that I am talking about, is theta. So that's theta, latitude of the place at that place. Now, the next question you must ask is, what is the radius of the circle along which I am moving at that place? The radius of the circle would simply be this radius. It would simply be that radius. Because this is theta, you can say that this angle also is theta. Or you can see a right angle triangle here. Here, theta sticks to the radius, so you can simply write that r cos theta. R cos theta is the radius of the circle along which you're moving when the earth rotates. The earth is rotating about this axis. Earth is rotating about this axis with an angular velocity omega, and that's why you are going in circles of that radius. Now, what are the accelerations that you are subjected to? You are subjected to an acceleration in this direction. Let me draw that a little longer. Now, that's g, acceleration due to gravity. I've drawn the vector from here because you're standing there. And because of this movement, you're being thrown away from the surface of the earth in that direction. Now, let me draw it with a better arrow. You're being thrown away in that direction, right? And this particular thing can be resolved. Let us resolve it in two directions. In a direction perpendicular to the surface of the earth, in a radial direction, and in a direction that's tangential. So we have resolved this vector into two components. Let me just make those components visible to you. Okay, so that's one component, and here is another component. Because this is theta, this is also going to be theta. I asked you what are the accelerations that you are subjected to. This is g, and this is going to be omega square times the radius. But I told you that the radius is r cos theta. R cos theta is the radius along which you're moving. So you can simply write that as r cos theta. R cos theta is the acceleration in that direction. You can resolve that again into two components. That's the radially outward direction and the tangential direction. This is the cos component. So it would be omega square into r into cos square theta, because it's this multiplied by another cos theta. So it would be omega square r into cos square theta. This would be omega square r cos theta multiplied by sine theta. This would be the component here. If you just see along the radius, acceleration due to gravity is acting in that direction, but the centrifugal accelerations component acts in the opposite direction. Now, what do you think is the net acceleration due to gravity at this place? This is certainly much greater than that. I mean, my vectors are not to graph. So, you can simply write that the acceleration due to gravity at that point is g dash, which is equal to this, because they are in opposite directions, you would simply subtract them, g minus omega square times r cos square theta. Well, we have the net acceleration due to gravity being g dash. It would be g minus omega square times r cos square theta. Now that is the relation for variation of acceleration due to gravity with latitude. At poles, theta would simply be 90 degree because that's 90 degree. Cos 90 becomes 0. So acceleration due to gravity would be 9.8, exactly 9.81. But then if you are standing on the surface of the earth on the equator, then cos 0 is what it becomes. Cos 0 is 1, and then you have acceleration due to gravity being g minus omega square times r, which means acceleration due to gravity is least on the equator. So acceleration due to gravity is not the same at all latitudes. It's going to be different at different maximum at poles and minimum on the equator. That's a piece of information for you. Having played around with this one, let us try to answer the question based on this one. The radius of the earth is 6,400 kilometer and g is 10 meter per second square. In order that a body of mass 5 kg weighs 0 at the equator, the angular speed of the earth is, that's the question to us. So we want the earth to be spinning so quickly that the acceleration due to gravity on the surface of the earth is supposed to be 0. If that is the case, let's say omega is the angular velocity and r is the radius. The acceleration due to gravity acts in this direction, but the centripetal acceleration is in that direction, whereas the equator, the centripetal acceleration is maximum. So we have the equation g dash equal to g minus omega square r into cos square theta. But because it is the equator, theta is 0, cos 0 is 1. So g dash becomes equal to g minus omega square times r. G dash is the total acceleration due to gravity, and you want the weight of the body to be 0. Mass is never 0. So acceleration due to gravity must be 0. So this is 0 equal to g minus omega square times r. Then you have omega square being equal to g divided by r, or omega being equal to root of g by r. If you substitute for this, you will have a root of g being 10 meter per second square, and the radius is 6,400 kilometer. 6,400 kilo is 10 to the power of 3. So 10 and this becomes 2. Simplifying this further, you will have omega equal to 1 divided by, that's 800. Because omega is in radian per second, 1 by 800 radian per second would be your answer. If you just see, then it is option C. Well, to conclude the video, with these questions having solved, let's conclude the video with a quick summary. The acceleration due to gravity is directly proportional to the distance from the center of the earth. So if you simply plot a graph, let's say this is your y-axis, and that's, let me similarly draw x-axis. Now this is your x-axis, place it here. Okay, now that's your x-axis, and you want to draw a graph for variation of acceleration due to gravity, then you would do it this way. Watch. All right, up to the radius of the earth, the physical radius of the earth, the acceleration due to gravity would simply linearly increase, but after that it would fall off as 1 by r square. So until the radius of the earth is reached, you can say that the distance from the center is r and acceleration due to gravity is g. G is directly proportional to r for small r less than capital R, and G is inversely proportional to 1 by r square for r greater than capital R being the physical radius of the planet, in this case the earth. So if you understood this graph, I think If you have a confusion of why G is directly proportional to R, it's quite easy to see that G dash is equal to G into 1 minus D divided by R. You can just take an LCM. Then what happens is R minus D divided by R. R minus D essentially is the distance from the center of the earth. So R minus D is the distance from the center of the earth. You can go back to the video and see that R minus D was simply the distance from the center of the earth. G dash becomes equal to G into R divided by R. Anyway, this G and R are constants. You will see that G dash would be proportional to R. So it's proportional to R inside, inversely proportional to R square outside. With this understanding of acceleration due to gravity, you know everything about how to deal with acceleration due to gravity in various cases. But do remember, the day you stop growing is the day you start decaying. Thank you.